Okay, so hubris. Okay, so basically, at about 1900, plus or minus 5 years or so, okay, physics was done. Physics was over. People were talking about the end of physics. Okay, Newton's laws describe the motion of planets, and if you knew enough calculus and could solve the equations, you could solve the motion of anything with Newtonian mechanics. Maxwell had done the same thing. He had applied calculus to all of electromagnetism, and it was he that actually came up with the speed of light being the square root of all these constants, right? Okay, so basically people were they were saying young men should not go into physics. Women, of course, definitely wouldn't go into physics in 1900, even though there were several famous women physicists, right? But young men were to be discouraged to go into physics because basically all of the discoveries that ever could be made had been made, and there you have it, right? Okay, and there were a few tricky bits to be worked out. One was that whole idea of light, the speed of light. What was it with respect to? But they had that figured out. It was light traveled through a as yet to be discovered medium called ether, right? We all know that, right? Okay, and the other problem was something called black body radiation, and nobody knew at the time that this was going to explode into quantum mechanics, but here we have it, right? Okay, and so this is a picture of course, Albert Einstein, right? And this is Max Planck. It's probably Max Planck, right? Because I bet it's not. There's no Max in German. So basically, black body radiation is the radiation given off by hot objects. This projector has a tungsten bulb probably, and it's glowing white hot, and that's how it can put out all the colors of the spectrum here. And there we go. And if you looked at a poker, if you stuck a poker in the fire, it would start to glow red hot because it would be this hot first, right? It would be 3,000 kelvins. And if you look at this graph here, this graph right here is the wavelength. So this is long wavelength. This is infrared, right? And off into radio waves. This is the relative intensity. So not all frequencies are put out with the same intensity, some more than others, and it follows a pattern. And it was that pattern that Planck was trying to figure out. Okay? Now, take a look at this curve. This is the curve for 3,000 kelvins. The first thing you might notice is that 3,000 kelvins doesn't glow very bright. There's not much area under the graph, yes? Not a very bright thing. It's glowing kind of a dull cherry red. The second thing that you might notice is that the peak of it, the most common wavelength given off, is in the infrared range, and here is the visible range of light, and it is much brighter in the red side than the blue side, correct? So we would see that as kind of a reddish glowing thing, and that's because it's not very hot. It's just glowing sort of cherry red, right? This guy here at 6,000 kelvins, though, this is going to be the peak is over here on the short end of the visible spectrum, which is right here, right? So it's going to be white hot or blue hot, yes? Okay? So this is a very, very hot thing there. Notice it's also much brighter, yeah? So this is things we notice, right? As it gets hotter, it also gets brighter, and it's this pattern that Planck is trying to figure out, right? And so he can't figure it out, and it's the middle of the night, and Satan appears in front of Max Planck and says, if you give me your soul, I will give you the... Wait, that's a different story. That's Faust, isn't it? I believe that's Faust, okay? So, no, here's what it is, okay? In the middle of the night, it's still the middle of the night, it's not Satan, it's mathematics rears its ugly head. Planck can't get his function to work, and here's what he's trying to do, okay? You need to understand, why do hot objects... Can we stop? Can you stop passing notes around? And yeah, okay. The first thing you must understand is, why do hot objects give off light at all? And the answer is actually quite simple. They broadcast electromagnetic waves the same way that an antenna does it. They take charge and they move it. And when you move the charge, don't you move the electric field with it? Yes, there you go. So why is the charge moving? Well, because hot objects have moving atoms, yes? Cold, hot, really hot, yeah? Right? So basically you just have all these atoms. They can have any energy they want, or at least that's what Planck thought, right? They can have any energy they want, and as they vibrate back and forth, the hotter they are, the higher the frequency that they do. But of course they're not all the same speed because of the hot objects. They're not, it's random, it's chaotic, right? And so that's what this comes out of. It's sort of almost, it's a distribution like that, right? Okay, now, what Planck thought was that vibrating atoms could have any energy they want, because why couldn't they, right? Classical physics is like the physics of the real numbers. They can be anything they want, right? Well, that didn't work. Especially it didn't work out here. Okay, we could not get the right answer out here, right? Now somebody might say, well, who cares? It's good enough, right? It fits the main part of it. Well, no, that wasn't good enough for Maxwell, right? So in the middle of the night, to get it to work, he says, look, I'm going to make the energy of these little oscillating atoms, I'm going to say that they can only be particular steps. He quantizes the energy, right? It's just a big word for saying that it's steps. And he put Planck's constant in there because he's making the thing. He can name it anything he wants. He named it Planck's constant, right? Okay, I don't even know that he did, right? Okay, this is the frequency with which the oscillator is vibrating, and then this is an integer, 0, 1, 2, 3, etc. Okay, and so he says that the energies are artificially quantized, just like the charge of an electron is. Yes, we're familiar with this, right? Okay. Now, is there any reason why energy should be, in a classical sense, only one thing and not another thing? It's like a baseball, right? If this were true for baseballs and we could observe it, the baseball could go 1 meter per second, and then if we kept putting energy into it somehow, right, or whatever, we could also go 2 meters per second, but we couldn't go 1.1 meters per second, right? Does this make sense to us? No, it doesn't really make sense, right? Okay, but Planck does that. Okay, thinking, by the way, that it's only a mathematical trick to get the right answer. He does it, and it's perfect. He does that, and he does the math, and he figures it out, and it fits exactly. It's perfect. Now, he still doesn't believe that energy of atoms is quantized, because why should it be? And this is an interesting theory of knowledge type question, right? If the only mathematical model that works quantizes energy, does that mean that energy can only be particular steps? Yeah. We don't know. We just assume that it is because that's the simplest explanation, is that it really is. Now, why it is, we don't know. This would be a good question you could ask your maker. Why is it that energy is quantized? I think don't you get a question? And a phone call too, right?
What if your answer
yeah.
is it isn't?
Why would he publish something that he could possibly?
Because it got the answer. See, okay. It's late at night. You're trying to get the answer for your homework. Assume that we care about our homework this much, right? The answer's in the back of the book. We had the data. He had the data, and when he did this, it fit the data exactly. And he assumed that some clever mathematician would come along and say, oh, you can get rid of the quantization by doing this. And nobody has. In fact, somebody's actually shown that you can't, there never is a hidden variable theory that will get rid of all this weird quantum stuff. Okay, I believe Bell is his name. Okay, so anyway, here is this idea, and it works, and Planck doesn't like it. Einstein adds to his anxiety by saying, look, okay, this is perfect. This makes sense. Light is actually made up of then particles. Einstein comes along and says, light is made of particles, and here's why. Because if these things can only give off energy when they go down, the idea is that the little vibrating oscillator goes from one energy to another, okay, it's always going to give off energy equal to the step size, yes? It's like you're dragging a box down this thing. It doesn't continuously lose energy. You drag it for a while, and then it goes bump, down a step, bump, down a step, yeah? Okay, and every time it gives off a little bump like that, right? Okay, it goes down a step, it gives off a photon, and the energy of these photons is Planck's constant times the frequency, yes? There we go. So this is the, put a box around it. This is our formula, right? And you should have that in your little note guide, yes, don't you? Okay. Now, obviously, if frequency is c over lambda, because it's always the speed of light, right, then we can say that it's also hc over lambda, which everybody in the world has this formula. Your book has the formula. Every textbook has the formula. Is it in the data packet? No, just memorize it or be able to come up with it quickly, because it's kind of vital, right? Nobody talks about frequency of light because it's in Bugalahertz, right? We always talk about nanometers of light. I don't know why. It's just a thing that people do, right? Okay. So, by the way, does the rest of the world say, Einstein, you're a smart man. You gave us the theory of relativity, so we therefore believe that light is a corpuscle?
No.
No, it was not believed for the longest time. It's an interesting story, that. Okay, it was not believed for the longest time because why? Because light was clearly a wave. Light, when it impinges on the surface of water, bends. This is because the wavelength shortens and the wave's fronts must be continuous, and so therefore it refracts. Only waves do that. Particles just hit the water and go splash or something, right? Yeah? Okay. Light, when it impinges upon the double slit, okay, some of the light goes through one slit, some goes through the other. Then